Okay, so for this session, I'm going to be talking about the economics of distributed resources. By right, engineering economics is a very lengthy subject and it deserves its own subject to learn about the principle of economics in engineering projects. But since I'm only going to talk about the relationship of economics with relation to a PV project, so I am just only going to highlight the key issues or the key concepts. So before we start with the key concepts, let's look a bit about the nature of electricity generation and consumption in Malaysia. So when we talk about cost analysis, we are talking about investment. How much do we need to invest in a project? And when we talk about investment, usually investors are interested in only one thing: how fast can they get back their money and how fast they can turn the money into profit, or they turn their investment into profit. So in order to do this, we as engineers need to know about cost analysis, or at least have a fundamental overview about how to calculate them. So an essential step in any economic calculation for any project is a careful analysis of the cost of electricity or fuel that will be displaced by the proposed system. Okay, so first we need to understand about the nature of electricity usage in the respective location. So now we are going to know a bit about Malaysia. Okay, this is obtained from Tenaga Nasional Annual Report way back in 2018, if I'm not mistaken. So it provides the distribution of energy consumption with respect to sectors available in our country up until financial year 2016. Okay, so we see some interesting patterns here. So the category of customer can be divided into 4 types as indicated by the colors. So the blue color is industrial, the maroon color or brown color is commercial, the green color is domestic like homeowners, and yellow is for others. Okay, when we talk about number of customers, 81.5% or roughly 4 out of 5 customers are domestic customers, right? Compared to industrial, of course, the number of customer from house owners are greatly more than industry. But when we talk about energy usage, we have 42%, roughly 42% coming from commercial industry, and 38% coming from industrial sector. So if we combine them in terms of sales and in terms of sales in terms of dollar, ringgit Malaysia, and sales in terms of energy, then industrial and commercial sectors dominate. They take about 75 to 80% of the total energy consumption. So these are the main customer for TNB, right? So for domestic users, as we can see from the annual financial year, they only contribute to about 20% of the TNB income or TNB profit. Majority come from industry and commercial. Okay, so that is the nature. I think that also applies mostly to any country. Domestic, the number of customer is more, but the usage is less compared to industrial and commercial. Okay, so with that in mind, now from TNB side, or from the utility provider, they need to consider, number one, what is the total energy consumption, and number two, what is the expected energy consumption for, let's say, this year, 5 years ahead, 10 years ahead. They need to plan, and they need to make sure that the total energy generation will always be enough. If there is a shortage, then there will be problem in the grid. So that's why they need to have some planning, and they need to make sure that they have enough reserves, so that in the future, because our energy consumption always increases every year, we use more devices, we use more machinery, we tend to use electricity appliances much longer compared to a few years ago. We have internet that may be on 24 hours. So all that involves electricity, and TNB needs to consider the increase throughout the year and for the future. Okay, so how does TNB manage the cost and the energy, the preparation of energy supply? So we need to understand the concept of load duration curve. Okay, for simplicity, we take the hourly energy demand in terms of kilowatt, so hourly power demand. So when we have hourly, so we get kilowatt times hour, right? So kilowatt times hour. In 1 year, we have 8,760 hours. So we classify them according to the amount of kilowatt for each hour. So we will have 8,760 bars, and each bar will represent the amount of energy that is going to be used at one specific hour. Now first, we will have the figure on top here, where we arrange according to chronological order. So chronological means time-based. We start from hour 1 of January, let's say January 1st, 2020, until the last hour of 31st December 2020. So we do this and we get the value for each hour, and we are going to know which one is the highest and which one is the lowest and which one is in between. Okay, so chronological, time-based, we know from this one when is going to we are going to use the highest amount of energy, and when the lowest, and when in between, right? So now we modify the figure and rearrange the bars into what we call as order from highest to lowest. So we rearrange. So the highest one we put on the most left side, like this one. And then we arrange the next highest, the second highest, the third highest, and so on until it reaches the lowest value. Now, why do we do this? We do this because we want to know what is going to be our load profile or load curve profile throughout the year, so that we can arrange our resources to fulfill them accordingly. Okay, here's what I mean. Now, once we have already rearranged from highest to lowest, we can obtain a figure like this. Okay, this is just an example. So let's say you get, after you rearrange from the highest to the lowest, you will get this figure. So what can you obtain from this figure? So first, let's go to the most right hand side. You see that this is going to be the lowest value throughout the year. And when we cross according to the y-axis, the value is 2000 megawatt. So this is actually the minimum amount of power that must be supplied throughout the year, 2000. So we call this as the base load, right? Because it doesn't go any lower than this. So this is the base load that needs to be there throughout the year. And then there is from the whole year, we have 1,000 hour where we have peak value, right? So we have from 6,000 to 5,000, we have 1,000 hours where we need to supply, but only for a short time, or the value for 1,000 hours here, we need to supply between 6,000 to 5,000. So this one is only 1,000 hours throughout the whole year. So this one, we need to have what we call as peaking plant. Okay, so peaking plant is when the sudden increase in the demand, so we turn on our peaking plant to supply power to it. Okay, for example, suddenly during afternoon in April, there's a sudden heat wave that is occurring throughout the country because of the weather. So everybody is turning on air conditioning at the same time. So there is sudden surge in power or energy demand. So TNB needs to be prepared for that condition, and they must have plant that can be turned on instantly and supply power if the user starts to turn on the aircon instantaneously or instantly. Okay, so this one is called peaking plant or peaking duration. Okay, so the rest of the time between 1,000 to about 7,000, so we have a decreasing value, right? So we can arrange the type of resource that we want to use based on the condition. Okay, we note that now because we rearrange according to the magnitude from highest to lowest, this does not occur in chronological order. Okay, so maybe in 12 afternoon, the value can be 6,000. Maybe by 2 p.m., the value can drop to 5,000, the demand. 4,000 or 3,000, the demand can drop. And then it can increase back again. So TNB needs to consider that, right? So if you look at the original figure here, when we arrange according to hour, actually it fluctuates. Sometimes it go up, sometimes it goes down, and then it goes back up again. So TNB needs to be prepared to consider when it goes up, then TNB needs to supply. When it goes down, then TNB needs to cut off the supply from generator. So this is a continuous process, right? Okay, so this is how we interpret the curve. Okay, now let's look at the cost of resource to or the cost of fuel to supply the electricity. So again, for simplicity, I'm taking this from a textbook. So we have, let's say, three types of resources. We have coal steam, we have combustion turbine, and we have combined cycle. So this is the figure on top here represents the cost related to hour. Okay, so if I go for coal, you see that the starting price is rather expensive compared to combustion turbine and combined cycle. But as the number of hours increase, you see that the price does not increase that much, right? It's rather, it's not flat, but the gradient or the slope is not that high. Now, when we look at combined cycle and combustion turbine, so we see that it started as low, means the price is low when the hour is low. But then the more you use or the more power you generate over time, then the price per kilowatt hour start to increase. And you see the intersection or the crossing point between the values here and here and here. Okay, so let's look at what this means. So the cheapest option between 0 to 1,675 hours is the lowest one here, which is the combustion turbine. Okay, so from this value to this cutoff point here, combustion turbine is the cheapest. cost. So we should use this as our peaking plant. Okay, so this is why we have the dotted lines here represent the the cut-off point. So we have combustion turbine at this value here. Now, after this value from 1675, so it's no longer economical to consider combustion turbine when we compare to combined cycle. But combustion turbine is still cheaper compared to coal steam up to this point here. So it's about a bit over 4,000 hours. After 4,000 hours, then combustion turbine is going to be very expensive. So we do not want to use it more than 4,000 hours. Right? So that's why you see, for combustion turbine, we want to use around 1,300 megawatt when it's the cheapest value. After that, we want to use 1,200 from combined cycle. And the rest for the base load, because the coal, the price does not increase that much even after thousands of hours. So ideally, coal is the best option for base load, to supply base load, because the price does not increase that much. So that's why we have, for the base load, we depend on coal. And then the second option, we depend on combined cycle because it's the second cheapest. And the last option is combustion turbine because it's the most expensive after this value. Okay, so the cut-off point is important. Now, this is the representation of the same figure in terms of capacity factor. Right, so for coal steam, we have a capacity factor of about 91%, so very high. Okay, so coal is a very good stable resource for electricity generation. And then the rest we have for the combined cycle is 47%, and for the combustion turbine is 10%. So in terms of cost, of course, for coal steam, the total overall cost is going to be the cheapest. As we can see here, the unit cost, because we generate a lot, so the cost per kilowatt hour is going to be only 4.69 cents if we assume the following condition. But for the combustion turbine, because it's a peaking plant, we need to have it prepared throughout the year, but we only use it for a short period of time. So the cost per kilowatt hour is more higher. Okay, so you have the note there. Electricity from the peakers is expensive because peakers are used so little. But you need to have them throughout the year. They need to be ready, but you don't use it that much. That's why the cost is higher per kilowatt hour. Okay. So renewables is not in this figure, but renewables has very low operating cost because it does not have any fuel. I mean, the fuel is free. But with it also has the weakness of intermittent operation. Like solar, it can only operate when there is good weather. And we cannot guarantee tomorrow there's going to be good weather or today is going to be good weather. So, by right, it should be dispatched first whenever they are available. So, even though their capacity factors may be low, for solar maybe only around 15%, they contribute part of the base load here, a small part of the base load. All right. So in the next section, I'm going to talk about load factor and how we calculate them.